If everybody could share in the chat, just which of these categories would you like to start with? Qubits, gates, circuits, algorithms, coding, or mystery category? Okay, I'm seeing qubits, gates, mystery category, mystery for. I aspire to be a Ken. I'll take it. Okay, let's see. I think mystery seems to be pretty popular, but we'll also make sure we get to gates and all of the others. But we'll start with mystery. Why don't we start with mystery? We will go for 200 to start. So, true or false, quantum computers are faster, more efficient versions of classical computers. Go ahead and share in the chat. Is this true or false? Okay. Yeah, we gave true or false as an answer, but in the true spirit of a quantum computing course, I suppose you could say a superposition of the two, a plus state. I will go ahead and say that this is false. There are some cases where this might be true. There are some algorithms that have been shown to be faster, more efficient than the classical versions. But generally, really, the key takeaway here is that quantum computers are different than classical computers. They're not just the next step up. They're not the supercomputers, right? Yes, exactly, Umar. The faster versions of classical computers really would be supercomputers, which are still entirely classical, but it's just like the best of the classical. Whereas here, it's just a nuanced thing. Quantum computers are just different, and there are some cases where they are faster and more efficient, and we're really interested in those cases. So it's still a very interesting and worthwhile case. Okay. So, all right, why don't we do another mystery category for 400? Why do we measure? Ooh, this is a deep question, I would argue. Why do we measure? Feel free to share any and all thoughts on this. Yeah, okay. So this is a much more open-ended question. It's not quite as plain to see as a true false, but I'm liking some of the responses I'm seeing. Yeah, so the why of measurement really is that if we don't measure, and this is true in classical or quantum physics, if we don't measure, we have no idea what's happening. And for our purposes, it might as well not happen at all, right? I mean, if we have this fancy quantum computer that we've spent so many years and so much money and so many resources and just energy putting together, and yet we have no way of knowing what's happening inside of it, it really does not seem worth it. I mean, we can do that, but it just seems like an awful waste, and it really doesn't give us any insights into what's happening. We cannot use it for anything. So from a very technical or a very applied standpoint, let's say, we measure because we want to use the quantum computer. We want to get computation out. Yeah, yeah, I like that quote, Wayne. Yeah, if a tree falls in a forest and no one is around to hear it, does it make a sound? And that's exactly kind of the case here. If your quantum computer runs an algorithm to break the most complicated cybersecurity protocol out there, and yet you can't measure it, not very useful. That's an awful waste. There's other reasons why we could argue we measure, but I would say that's probably just the clearest. So we need to measure in order to actually use our quantum computer. That's the only way we get results, as many people pointed out. That's really kind of another way to say it. We need to get results, or else there's no purpose of it. Now, an outcome of measurement is that it stops superposition. It collapses superposition is the technical terminology. Okay, so I believe there are a few requests for gates. So why don't we go there? Let's start at 200. True or false? The X gate makes a 90-degree rotation around the X-axis on the block sphere. I'll give everyone a minute or two to answer. True or false? Okay, yeah, I don't seem to have tricked up anyone here. It's okay if you didn't get this, but yeah, it seems like we're pretty comfortable here. It is indeed false, as some people pointed out. The problem here is it's an 180-degree rotation, or if you're using radians, then it's pi radians, but it's a 180-degree rotation around the x-axis, but everything else is correct. So this is almost a correct explanation. In fact, we would call this the square root of X gate, which is a real thing. But this is not an accurate depiction of the X gate. Okay. Yeah, are people keeping track of their scores so far? How are we doing? Got 400, 600, okay. Okay, so why don't we do a circuits one? Let's move up the stack. Okay, circuits for 200. What is a quantum circuit made up of? And here I'm looking for 3 elements in particular. What is a quantum circuit made up of? What are the 3 elements that we typically say a quantum circuit is made up of? And you need all 3 to get this correct. Okay, very nice, very nice. Yeah, so the 3 parts that we typically break up a quantum circuit into are indeed the qubits, the gates, and the measurements. Exactly. So we start with our qubits in some sort of state. Then we apply a series of gates. And at the end, we measure a number of qubits to see what state they ended up in. That is a generic quantum circuit. As Amar pointed out, algorithms are just really a smart way to do this. So algorithms are an intentional, very specific, smart way to do this. Quantum circuits are just generally anything. But yeah, okay. Any questions about that? Yes, let me share maybe in the chat. So the answer is states, or I'll just say qubits, gates, and measurements. These are the 3 parts of any quantum circuit. Cool, quantum circuit. Yeah, so qubits, gates, and measurements. So this is a good question. Gemma asked about entanglement. Yeah, so superposition and entanglement and interference, these quantum properties, these are essential pieces of or properties of quantum states that we hope to use. the way that we try to get them is through the gates, and the way that we check if we got them, in some sense, is measurement. So we use gates in order to try to get entanglement. So in some sense, entanglement and superposition are what are created by quantum circuits, but they are not necessarily the three parts that make them. Ooh, this is a good question. Ooh, Chris, yeah, asking the hard questions here. Isn't measurement not possible without classical bits? It's true. You need some sort of classical system to store them in. I'm going to go ahead and give a bit of a cop out here and just say that I'm assuming that part of the measurement protocol is that you have classical bits to store the results in. So I know that's a bit of a cop-out answer, but let's say that measurement here is not just the process, it's also the apparatus, how you store them, the classical bits. But yes, if you really want to be very generic and more straightforward, you might say you have states, gates, measurement, and classical bits for your measurements. Okay. All right. What category would we like to go to now? What category would we like to? So someone's asking, so Jimmer, just about entanglement. Yeah, entanglement's a tricky one. It really takes a while to really sit with. Generally, the idea is that entangled qubits or entangled quantum states are ones such that one quantum bit, for instance, one qubit, influences the other one. When you know the state of one quantum bit, you know the state of the other quantum bit. For instance, you and I could both have qubits. We could prepare them in a special state and then go our separate ways. Based on that special state, if it had a special kind of entanglement, then we could force it so that when I measured and got, say, a 1, that I would know for a fact you got a 1 and I would not even need to ask you. But I could have an equal chance of measuring 0, and then I would know for a fact you had 0, even if we didn't talk about it or ever communicate that. So entanglement is a way for there to be this deep relationship between the states of systems, even when they're in superpositions. I think that's the key thing to me that separates, say, entanglement from just normal correlations or relationships that you can get classically. You can get similar types of things classically, they're just not as strong. And really the biggest difference is that even if your qubits, multiple qubits, are in superpositions, where there is absolutely no physical possible way to know in advance what outcome you're going to get, you can still ensure that whatever outcome you get, 50-50 shot, 0 or 1, that will be identical to the output I get. And that's a pretty wild thing, actually. That really should not be the case. If I have no way of knowing 0 or 1 beforehand, because it physically is both of those at the same time, it's awfully strange that somehow you could have something that is a 50-50 shot of 0, 1, no way of knowing beforehand. They're both 0 and 1, and I also have that, and yet we will always get the same thing. So yeah, entanglement is two bodies being influenced by each other, even if they are light years away. Yeah, now it is true. I think the flow here is very nice. Entanglement must come in proximity. You have to bring physical states together or systems together to entangle them in the first place. But once you've entangled them, then they can separate and they won't lose that relationship unless they're subjected to noise. So entanglement is another one of those things that noise is constantly looking to destroy, and why we want to isolate qubits and other parts of our quantum computers. So entanglement requires that you have these qubits close to each other, but then so long as you are able to keep them nice and isolated and error-free or noise-free or fault-tolerant, you can then bring them as far as you want, and they will have this relationship. Yes, the argument you'll hear is it's very important that there's no faster than light communication occurring here. Information physically cannot travel faster than the speed of light. That's actually a law of physics and something that can be quantified and measured, information and how fast it's traveling. Entanglement really is about setting up a relationship when you're close that exists when you're far that would not exist classically. We'll actually see some cases of this next week and in the next semester as well. But one thing I will say that I think is easier to understand about entanglement, or to start seeing about it, entanglement requires you have more than one qubit or more than one physical system. There's no sense of entanglement within one qubit because it's really about a relationship between different things, different quantum systems. Okay. So let's see. And I'm loving this comparison to, or analogy with socks here. I think that's a great one. Okay. So where would we like to go next? Where would we like to go next? Which category would we like? Qubits, gates, circuits, algorithms, coding, mystery category. Ooh, coding. Yeah, I agree. Okay, we'll do some coding, some gates, some algorithms. All right, why don't we jump in? Why don't we get a little more tricky here? Let's start at, let's start 600 for coding. So I'm going to give you a moment. This is actually perfect given our discussion about entanglement just a minute ago. Does this circuit produce an entangled state? So this may take a moment. There's a few lines of code here. Take a moment to look at this and answer. The answer is yes or no. Yes, it does produce an entangled state, or no, it does not. Okay, so we've got some answers, some questions, some comments. I like it. So it seems like everyone's pretty universally in agreement that this creates an entangled state. And I will go ahead and say, no, it does not. I was able to finally trick you all. No, this does not produce an entangled state. I'm curious, can anyone tell us why? Or why did we get tricked up? Yeah, so the circuit that you're outlining there, Wayne and Amar now, yeah. The key here is that, and I'll get my laser out here to point this out a little more specifically. Exactly, people are starting to pick up on it. Notice that the H is after the C naught. So up until that H gate, everything is actually pretty much what we would call classical. We're still working with the qubits and a quantum system, but very importantly, the first gate we apply is an X to the 0th qubit. We're just flipping it, right? That's actually pretty much a classical action, right? We take a 0 and we flip it to 1. We could have just done that with a classical bit and saved all that money and time. Then we apply a C naught. C naught on its own, or a CX on its own, is actually just kind of a classical thing. We know for a fact that provided there's no noise or errors, the 0th qubit after this first line, QC.X of 0, the 0th qubit will be a 1. And then we apply a C naught. Because the 1 we just flipped to 1 is a control bit here, we have a 1 as a control bit, meaning we will apply the X and we do flip the other bit. And so we go from 0, 0, and I'll write this in the chat, to 1, let's say 0, 1. The ordering is always a little funky, but let's say 1, 0. How about we do this just to make things very clear? Q0 will be 0 and Q1 will be in the 1 state. That's how we start. And then after we apply the X gate, we get this. So we apply, and sorry, the first state is Q0. Can I edit that? No. The first state should say that we started in 0 for both Q0 and Q1. And then we apply the C naught, which says that Q0, well, that doesn't change. Q1 now does change. And then we put the first one in a superposition. So we get the minus state and the Q1 gets in a 1 state. So in fact, this is the outcome. And again, just to be clear, my initial state preparation was a little off. They should both be in zeros, 0, 0, Q1 and 0 as well. So in fact, we end up with this circuit where this state where the 0th qubit is in the minus state. It is in a superposition that's fundamentally quantum. But the first qubit 1, is in the 1 state. That's fundamentally classical. There's no deep relationship here. No matter what you get for your outcome in measuring Q0, it will not be related necessarily to Q1. Right? Q1 is steady and always 1, whereas Q0 has this 50-50 chance. There's really no relationship you could describe there other than just describing them separately. Entanglement requires that there is in fact no way to describe the outcome of measurements without knowing the state of the other. That's another way of looking at it. So in fact, to answer, this is a case of a non-entangling circuit. It has a lot of the right elements, but just not in the right order. We would really need to flip or at least move this H gate, this Hadamard gate, before the C naught. A C naught or CX on its own does not create entanglement, nor does just a single H gate. We really need the combination. It's the combination of an H gate and a C naught in that order. So H and then CX creates entanglement. CX and then H does not. That's basically the summary here. The X gate is kind of irrelevant to this. We could have it or not. It's a bit of a red herring, let's say, just something to throw you off. We could have that or not. We could add it before or after. It'll slightly change the type of entanglement, but either way, it'll be there. So, okay, how do you know if your qubits are entangled? It's a good question. Depends a little bit by how we want to define that, let's say. If you know ahead of time what the entanglement is meant to look like, then you should have a good idea afterwards. For instance, you might have an entangled state where the two qubits must disagree with each other, right? That's a possible entangled state. The qubits must disagree with each other. I measure a 0 means you must measure a 1 or vice versa. In that case, if I measure a 0 and you measure a 0, we know there's a problem. We know we did not get entanglement. However, if we don't really know what type of entanglement we're supposed to get, or we're not really confident that we got different states because they're entangled rather than just randomness, really we need to measure many times. The only way to truly know that you have entanglement is to measure many, many times, to set up the same circuit, rerun it, and remeasure it every single time so that we can look at the overall statistics and see, does it make sense? Are we really only getting entangled results or results that are consistent with entanglement or not? There's subtler ways to see this. Some quantum protocols, for instance, or algorithms really rely on entanglement to work. So in some sense, if your protocol doesn't work, then you might not have entanglement. But if it does work, then you know you have entanglement. So it's kind of if you need to use entanglement for something and it works, then you know you have entanglement. But with all these quantum properties, it's really tricky. You can't just open up the box and say, hey, is my Schrodinger's cat in both states, or are my Schrodinger's cats entangled? Unfortunately, quantum physics does not allow us to do that. Nature is a little more fragile about this thing. And so we need to measure many times. Okay. Yeah, Chris, that's a good example. For instance, if you want to know, let's say I'm giving you a coin and you don't know, did I give you a fair coin that's going to be 50-50 every time? Or did I give you one that's going to be one more often? If you flip it a single time, there's no way to really know. You have to flip it many, many times in order to get a sense of what's going on with the coin. This is the same for entangled states. Entanglement really is a very special type of statistics, let's say. It's a statistical correlation if we want to be technical. Entanglement is a statistical correlation between states that is not possible using only classical physics. Yeah, so let's see, Mario, you're describing here. Superposition is created by H, true, and then Cx simply joins two qubits. If they are joined in superposition, they both don't go into superposition. They both don't go into superposition once when we apply H, that's not entangled. I think that might be flipped, Amar, but I also might be misreading. We need to apply the H first in order to get our control specifically into superposition. If our control is in superposition, that means that what happens to the target qubit is also in superposition. So in some sense, the action of the circuit actually depends on a superposition. There's a 50, basically our target qubit is in a superposition of having had an X applied or having nothing done to it. And because it's in a superposition of having different things done to it, depending on what the 0th qubit was, that it creates entanglement. It's because the outcome or what happens to one qubit fully depends on another one that's in superposition. Okay. Let's go back. Let's see, I think we haven't done much with algorithms. Let's go there. Let's start at the 400. So some of these may be a little tricky, but let's see. Which quantum algorithm is designed to factor large numbers? Does anyone happen to remember? I'll give you a moment or two to think about this. Yeah, this one's a little trickier. You know, we haven't really dug into this. We will likely look at it next semester. It is indeed Shor's algorithm. Peter Shor created this algorithm or discovered this algorithm in, I believe, 1995. And that is one of the often quoted algorithms for quantum computers. It is extremely efficient compared to classical alternatives. However, unlike Grover's, it's actually not provably better than classical computers. We just have never found a classical algorithm that beats it. It could be out there, we just don't know. Most computer scientists think it's unlikely, but we haven't been able to prove it, and people have been trying to factor numbers for as long as they've had numbers, more or less. Factoring is a very old thing, thousands or more years old, and yet we still haven't found something as fast as this classically, and so we tend to think it doesn't exist. Whereas Grover's, we know for a fact it can be proven. And as a reminder, Grover's helps you search in an unordered space. Let's say that can be a database. It can also be, for instance, our maze example. If you're trying to find the best way through a maze, you could consider all options and then get the ones you don't want to cancel each other out using Grover's. And other types of things like that. This is, in fact, could be applied to many other things. Okay. Let's see. Let's do another algorithms. Let's do the 600. Ooh, so I just mentioned Grover's, and I know we haven't dug too deeply into this. So again, I expect these to be a little more challenging. But what do you think? True or false? Can we implement Grover's search algorithm today? Okay. Yeah. So it's completely fair to say that you have no idea or you're not sure. Um, also say this is a somewhat subtle question. I would say we cannot implement Grover's algorithm in a meaningful way. We do not have a large enough or powerful enough quantum computer that can do this in a meaningful way, meaning we can use it for something. However, we can do it for small examples just to prove that it works a certain way. But in many of these examples, the time and the energy and the cost just make no sense compared to using classical computers. Uh, However, technically we can implement it, and we will likely see that next semester as well, as how we implement it and what the specifics are and all of this. Um, it's also very famous, again, just as one of the few provably better than or than classical algorithms. Okay. I believe I saw Chris asking for the $1,000, the max category. Let's do it. All right. Name the quantum protocol that allows us to send the equivalent of 2 classical bits with 1 qubit. And just to make things a little fairer or easier, I'm going to list the 3 options. I will say that there is teleportation, super dense coding, and QKD. So we saw QKD, but we had mentioned 2 other ones. And I will say it's one of these 3, a quantum protocol that allows us to send the equivalent of 2 classical bits using only 1 qubit. Yeah, it's super dense coding. So although we're not familiar with these, so it's fair if you're not sure, as some people have pointed out, it is the super dense coding kind of gives it away. Um, uh, exactly. So super dense coding, basically the idea is that you can almost densify the amount of information you can send. So only using 1 qubit, you can get 2 classical qubits. This is super dense in the sense that you literally actually provably cannot do this with classical computing or protocols. You would need at least 2 classical bits to do this. And so you've kind of compressed them in a certain way. Okay. Let's see. Let's go to a different category. I don't think we've done qubits. Let's keep it a little difficult, but we'll go more towards the middle. All right, let's go 600. Qubits for 600. What is the property that allows qubit states to interact constructively or destructively? Ooh, I'll give you a moment to. Yeah, very nice. I'm seeing the answers roll in. It is indeed interference. Yes. So they interfere constructively or destructively. This fundamentally comes about from the wave particle duality, or at least that's a very easy or natural way to see it from a physical standpoint. Although again, it's a very strange thing that it occurs. Okay. Yeah, interference is, well, keep in mind that when we talk about physics, interference can be a productive thing. Interference really just means that states interact with each other in some way and can be constructively added, so they create something bigger and better in some sense, or they destructively, they cancel each other out. But yeah, okay. Let's do some more qubits. Let's go down to 400. soften it up a little bit. Qubits for 400, true or false? One unique characteristic of quantum mechanics is that we cannot predict with absolute certainty what state a quantum object will be in. True or false? Okay, very nice. Yes, indeed, it's true. It is true. This is indeed one of the very important, unique characteristics of quantum mechanics that we use to our advantage, and at the same time makes it awfully difficult to work with quantum computers. Okay, qubits for 1,000. Ooh, we want to keep going with qubits. Okay, qubits for 1,000. A qubit has experienced blank when it loses its quantum state. And then I'll give you the hint that you should think back to our noise and errors discussion. So what do we say a qubit is experienced when it loses its quantum state? This one's tricky, but I think we got it. Yeah, so we would say decoherence. We would say decoherence. That is the most specific name we have for it. Really, when we're talking about a quantum state and it loses its quantum state somehow, for instance, why don't I give an example to make it a little clearer? If you have a qubit and it starts in a superposition, or you apply an H and it gets into a superposition, so it's in the plus state, let's say, naturally over time, the environment is going to basically take away that quantum information, that quantum state. And so over time, the quantum state would go from, say, plus to 0 or plus to minus. So decoherence is this property of taking away the quantum state from something. So for instance, taking away the superposition from a qubit. Now, I do want to point out, I believe Eloise pointed this out. Actually, both of your answers were correct. Really, at the end of the day, what's going on here, why this happens, is we say that the environment is in some sense measuring the qubits. Basically, the environment is measuring the qubits, and that causes the state to collapse. So really, with quantum computing, the game is all about keeping anything else from measuring the qubits except for you, and only when you want to. But in fact, we can view all noise and errors as fundamentally coming from measurement. That's really what they are at the end of the day, but it's just a funny way to think about it, because it's not like we are going and we have a special apparatus and we measure, and usually measurement is difficult. But because the environment doesn't care what it's measuring, in some sense, it just kind of recklessly measures all sorts of things and can cause the quantum state to collapse. Now, this is decoherence, when a quantum state is lost, basically. A qubit loses its quantum state, so it loses superposition or entanglement. On the other hand, relaxation is specifically when the qubit starts in the 1 state and ends in the 0 state. That is the more specific thing that is relaxation. It's in some sense a more classical phenomenon, right? You're just going 1 to 0, but some of the reasons why it happens are still quantum mechanical. But in some sense, I like to think of decoherence as losing your quantum information and relaxation as losing your classical information. It's not a perfect breakdown, but that's roughly what's going on. Jeremy, this is a good question. Why are we saying 1 to 0 instead of 0 to 1? So usually we encode 0 and 1 in a physical qubit by putting it into two different energy levels, like low energy or high energy. If you imagine a switch or like a classical bit, you could imagine the 0 is the switch off and the 1 is a switch on, but it's a quantum mechanical switch, so it can be in a superposition. So basically, over time, there are natural things that occur, the environment interacts with the qubits, and that one state, that on, gets switched to 0. But that is much more preferable because the one state has energy to give in some sense. It's in this high energy state. Things in nature don't like to be high energy. It wants to naturally relax into the calm, relaxing 0 state. And so we literally say that it goes through relaxation. It relaxes from the high energy 1 state down to the 0 state. Okay. So we have hit our time. I'm curious for folks to share how much money they got, quantum money, let's say, where if you measure it, you lose it, unfortunately. But yeah, I'm curious to see what you got, or if you have any last questions. But we can, in fact, end it there. And yeah, I'm glad to answer any questions, but you are free to go otherwise. And again, I would also love to hear how much quantum money you got here. And otherwise, have a lovely day.
So Adam, is there no homework assignment this week?
No, there will not be. Since it's a review week, the main goal is for you to actually look back at old assignments and to just review, recap. If you have any outstanding, then now is the time to go through it. So we wanted to make sure you really had this week just to focus on that. So yeah.
Okay.
Yeah, good question.
And the whatever this is called, the attendance quiz is wonky and giving fractional points. Like it matters.
Okay, sure. No, that's good to know. Thank you for pointing that out. I'll pass that along. Yeah.
All right. See you, Adam. Thank you.
Thank you. Okay.
Will we continue to review it in the following lecture?
So in the following lecture, we're going to kind of wrap up this semester by talking a little bit more about what quantum computing looks like today and where it's moving in the future. So it won't be any too in-depth discussion necessarily, but it'll be kind of a big picture overview of that. So we won't necessarily be continuing to review. For folks that are continuing on into the second semester, we will have more chances to review, particularly as we dive into some more complicated and technical things. But yeah, really, this is the week to review everything, just ask questions, all of that, and just kind of reach out if anything is still confusing. And yes, I'm not exactly sure for folks that maybe are set up to be in just for one semester but are interested in continuing on. I believe you can. I will go ahead and say probably the best place to do that is through the help link. But if you're also interested, if you're in that situation, let's say, I can pass along your name and make sure that gets sorted. But yes, I believe in the help form, you can do it. I want to make sure I get you the link for that. But yeah. All right. Have a lovely day, folks. It was wonderful working with you all. This was a fun lab, and I'll see you all next week. Yeah.